Rolling good. Okay. Hello, everyone. Thanks very much for having me here. So I'm Kong-Yi Su, graduate student from Caltech. So I'm going to talk about suppressing the cooling flows in massive galaxies with turbulent steering. So this work is majorly done with Phil and Chris. Okay, so this is a bad cartoon I made for the cooling flow problem. So in larger L-star galaxies or clusters, we typically find strong X-ray luminosity. This will imply strong cooling flows. Given the strong cooling flows, we might expect there's a significant amount of low-energy gas. However, in observations, we don't find those. So perhaps all the low-energy gas form stars, so there should be sufficient star formation. However, this kind of galaxies are typically quenched, and the star formation rate is low. Okay, so this tells us there must be some sort of heat source or pressure support to compensate the cooling flow. In simulations, the cooling flow problems typically present as too high star formation rate. So this is a simulation for 10 to the 14 solar mass halo with cooling flow problems, and you can see at redshift 0, the star formation rate is too high. There has been several non-AGM feedback solutions proposed in the literature to solve the cooling flow problems, which include stellar feedback, especially like Type 1a supernova or AGB winds, and also magnetic field, conduction, cosmic ray feedback, and morphological quenching. So perhaps any of these could provide sufficient energy or pressure support to compensate the cooling flow. However, we actually test this in isolated idealized galaxy simulations ranging from 10 to 12 to 10 to the 14 solar mass. And you can see none of the galaxies is quenched. We actually go through each of this to test why each of these mechanisms doesn't work, and this will be appear on archive soon, and I'm happy to talk with you about this later after the talk. So given that the non-AGM solutions doesn't work, we definitely need AGM feedback. So we test various AGM feedback model on top of the fire stellar feedback. Instead of having a more realistic AGM model, we test different kind of toy model, investigating different kind of energy injection and inject a different energy in different range. So we want to see that whether any kind of energy could possibly quench the galaxy without resulting into unphysical galaxy properties. And if any of them doesn't work, would it require unreasonable energy? So as a reference, so we testing on 10 to the 14 solar mass halo, the cooling luminosity of this will be like 10 to the 44 Earths per second. So these are the AGM feedback toy model of test in this work. So we have momentum injection, thermal injection, turbulent steering, and cosmic ray injection. So for momentum injection, we just dump the momentum with fixed flux to the black hole neighborhood. For thermal injection, we test difference in different case. So one of them is uniform thermal heating, and one of them is like limiting the thermal heating within like 30 kiloparsec Gaussian kernel, and also test the case that we just dump all the thermal energy around the black hole. For turbulent steering, we just manually externally steer up the turbulence with the mode like 100 kiloparsec. And again, we test the case that with uniform turbulent steering and with the case that confine the turbulent steering within 100 kiloparsec. For the cosmic ray injection case, although the cosmic ray is dumped around the black hole neighborhood, the diffusion of the cosmic ray, the diffusion coefficient actually decides when the cosmic ray, where the cosmic ray start to be significantly thermalized. And here we use like 10 to 29 in CGS, and this will translate as like significantly thermalized after you reach like 30 kiloparsec. So first of all, momentum injection. So we test the case with different momentum flux from 10 to the 34 to 10 to the 36 in CGS. So this is the resulting star formation rate. The black line is the default line. As you can see that the run with lower momentum flux doesn't actually affect the star formation rate by much. Whereas the run with significant momentum injection, there's not even a star forms in these simulations. So the gas is completely quenched, but it's only quenched by blowing everything away, as you can see in the bottom right panel. In this run, there's basically nothing left at the core of the galaxy. So for thermal injection, as we say that these are the case that with uniform thermal heating, and also the core runs are the run with like thermal heating confined with a 30 kiloparsec Gaussian kernel, and also the runs like dump all the thermal energy around the black hole neighborhood. The tested energy, the flux range from like 10 to the 43 to 10 to the 45 Earths per second. So again, this is a resulting star formation rate. The uniform thermal heating run doesn't do anything, as you can see here. Whereas if you confine the thermal heating with the same energy flux to a smaller kernel, it could significantly suppress the star formation rate. And also, like for example, in the black hole neighborhood case, the suppression is very significant. However, does any of this result in non-physical galaxy properties? So here we plot the density, temperature, and the turbulent velocity of each runs. So as you can see, again, the uniform heating run doesn't do anything, since for most of the gas, the thermal injection is still lower than the cooling rate. Whereas if you dump all the thermal energy around the black hole neighborhood, it very easily leads to overheats. And also the turbulent velocities drive to over 100 kilometers per second. If you smooth the heating through a 30 kiloparsec Gaussian kernel, the overheat will be less significant. However, the negative temperature gradient is still very hard to avoid. So then, cosmic ray injection. Again, as we mentioned in TK's talk, we include streaming, Hadronic and Coulomb loss, and the diffusion, we said is like 10 to the 29 ergs per second. And we test the flux with 10 to the 42 to 10 to the 44 ergs per second. So this, again, is the resulting star formation history. So as you can see, cosmic ray injection will also significantly suppress the star formation rate. This is typically done by a combination of both suppress the core density and also heat up the core gas. However, compared with the thermal heating runs around a black hole, you can see that cosmic ray is more efficient in suppress the gas density, and it doesn't lead to as much overheat at the core, since the cosmic ray diffusion pays the heating out. So finally, the turbulent steering case. Again, we say we have the turb low run and turb high run are the uniform turbulent steering case, and the core runs are the run with suppressed large radius turbulent steering. So from 1 to 4, the energy inject within 100 kiloparsecs goes up. So this is the resulting star formation history. Again, the top panel is the uniform case. The bottom panel is the case that we suppress large radius turbulent steering. As you can see, the star formation rate could be significantly suppressed in both cases. However, there's various constraints. So for example, if you uniformly stir up the gas, and the gas at large radius will be stirred too much, and it's easily a lot of gas is thrown out of the halo, and you can also lead to a significant suppress of the X-ray luminosity. This could be avoided if you confine the steering within like 100 kiloparsec. However, if you steer too hard, it can also lead to significant high Mach number. However, despite this, there's still plenty of space that could possibly turbulent steering significantly suppress the star formation rate without leading to too wild galaxy properties. So how does the turbulent steering works? So first of all, you might think that turbulent heating could possibly heat up the gas. However, the inject turbulent energy in all of the runs is like at least 2 orders of magnitude lower than the cooling rate. So this only does like less than 1% of the work. A more important thing is the mixing. So here we track the particle as in a certain snapshot as originally cold and dense, and see in a subsequent snapshot how much of them remain cold and dense or form stars, which is the black line, and how much of them become hot or mix into large radius. As you can see, more than half of the gas particle is mixed by turbulence into a hot halo. Another important thing is that by combination of mixing and also turbulent pressure support, the core density is suppressed, and this by itself lower the cooling rate of the core and also significantly enhance the cooling time. This also do a lot of the works. So summary, non-AGN feedback model would only have a minor effect in which we investigate stellar feedback, magnetic field conduction, cosmic ray feedback, and also morphological quenching. Whereas in the AGN aspect, it can possibly do a much large work on the cooling flow problems. So for the AGN toy model, we inspect isotropic momentum injection, thermal heating, turbulent steering, and cosmic ray injection. The isotropic momentum injection either does nothing or punch a hole at the core of the galaxy. The thermal heating, it can possibly suppress the star formation rate. However, it very easily leads to overheat. The turbulent steering could suppress the star formation rate through a combination of mixing and puffing up the gas. However, this should be confined within like 100 kiloparsec. Otherwise, you also significantly lower the X-ray luminosity. Finally, the cosmic ray injection could also suppress the star formation rate through a combination of heating and puffing up the gas. So we conclude that the stir up the turbulence and inject cosmic ray could be an important aspect of a potentially more realistic AGN feedback model and could possibly solve the cooling flow problems. So thanks very much for listening.
Some questions?
Sorry, I wasn't clear. The turbulent stirring mechanism, what is actually doing the stirring?
So we externally stir up the turbulence. So
No, but I mean, in a real object.
There's potentially various ideas that could possibly stir up the turbulence. So for example, like jets or processing jets. Yeah. But here we didn't go into how the turbulence happened. We just see what it could be.
More questions for Keng-Yi? If not, let's thank Keng-Yi and thank all the speakers this morning.
Okay, before people go out to the coffee